We may be interested in predicting sentiment of movie reviews or fitting a line to some points. In both of these settings, we typically have a dataset to learn from where each data point is associated with a label. Recall that we refer to learning from a dataset where every data point has a label as supervised learning. In this situation, we would ideally like to learn a model that maps points from the underlying distribution X of data points to their labels Y. However, we are given finite dataset D to learn from, and so we will try to use this data to set parameters theta such that this map performs well not only on points in the dataset, but hopefully also any other point we can sample from the underlying distribution. Also, recall that we find parameters which maximize probability of the parameters given the data. This is maximum a posteriori estimation. But in order to accomplish this, we will have to convert our maximum a posteriori problem into an equivalent problem which we can work with more directly. Here are the assumptions we will make. Data in the dataset comes from a Cartesian product of x and y. In other words, each data point contains data from distribution X and an associated label from the set of labels Y. We also assume that our model F can learn to map X to Y, or at least to some reasonable degree. When dealing with actual problems, we need to think about whether or not it's appropriate to use a particular model or not. For example, we can try to fit a line to parabolic data, but that mapping won't do so well. In the conversion to a more manageable equivalent problem, we will make the assumption that each data point in the dataset is independent from one another. In most cases, we make the assumption that the label depends on the data points they are associated with. For example, we would assume that a label of cat or dog depends on what's in the picture. There are cases where you might instead assume that both the data point and label depend on some unobserved information. Note that this would result in some changes to the derivation I will show next. We will start off with our problem of maximum a posteriori estimation, and use Bayes' rule to express the posterior in terms of other probabilities. Now, the probability of the dataset, or the evidence, does not depend on the parameters theta, so it is a constant with respect to the optimization problem, and we may drop it to form an equivalent problem. Let's expand the dataset into index notation so the probability of the dataset given theta is the joint probability of each of the data points given theta. We will now make the assumption that each of the data points is independent, and so the joint probability is equal to the product of the independent probabilities. Since log is a monotonic increasing function, it doesn't change the optimal point of the optimization problem with argmax, and we can compose our term with it to form an equivalent problem. We can use the properties of the logarithm to split up this giant product of probabilities into a sum. Remember that we assume that the label depends on the data point for all data points, so it's natural to re-express the probability of xi and y sub I given theta as the probability of y sub I given x sub I and theta times the probability of x sub I given theta. We'll use the properties of logarithms to again split up this term on the left, and this will be the final expression which we will analyze for the rest of this video. In the derivation we just did, we composed our term of interest with the log to form an equivalent optimization problem. But why does this work? Suppose we have a strictly monotonically increasing function g. This means that given two values a and b such that a is less than b, then g of a is less than g of b. The same goes for when we have values h of a and h of b, where h is some other function. Then g of h of a will be less than g of h of b if h of a is less than h of b. For our particular situation, we are dealing with a function of theta, which would be h in our example, and log is a monotonically increasing function, which would be g here. The function evaluated at optimal theta will have a value greater than evaluated at other values of theta, so putting a log around it will therefore not change the optimal value. Looking at the final state we arrived at, notice that the last term came from the prior p of theta from when we used Bayes' rule to re-express the posterior in terms of other probabilities. So this term is usually called the regularization term. I'll explain regularization another time, but for now you can think of this as a way of biasing the outcome of the optimization problem depending on what we believe about the parameters prior to seeing the data. The first two terms would be on their own if we had started from maximum likelihood estimation. Recall that maximum likelihood is the same as maximum a posteriori when the prior is uniform. The first term here is typically seen on its own in explanations of maximum likelihood. This is because it's frequently not clear what to do with the middle term here. It's frequently assumed to be uniform and therefore dropped. A little note on the middle term that we just dropped. This is for more advanced viewers. You may recognize this term from self-supervised learning and transfer learning. There's likely a connection to be made there. We could view self-supervised pre-training as training this term only, maybe on a larger dataset that's close to the data distribution X, to try to get a better estimation of parameters.